Okay, we're going to start. We're going to finish up 4.2, which was maximum and minimum values. So we looked at last time two kinds of maximum and minimum values. There was the absolute maximum and min, which is the largest value or the smallest value in any interval respectively. And there was the local maximum and minimums, which were in some local region when you zoom in who's the largest and the smallest. We also looked at the closed interval method, and we did an example of that, where we can locate an absolute maximum and minimum. Now I'm going to show you how to find a local maximum and minimum. There are two main methods. So one is the first derivative test. The second is, surprisingly, the second derivative test. There was a point where I gave you this huge table about the original function, the first derivative and the second derivative, and what information it tells us and how it tells us, where I kind of basically described these both, but I just want to reiterate it and make sure that we're getting the right conclusions from doing them. So let's go over the first derivative test. And I should probably mention the original function. Yeah,
Just a quick question. When's our final?
I don't.
No, it's the same day as Chem.
So the 8th?
Yeah.
Okay.
Yeah, one of the them is the 8th, one is the 13th. I forget which is which. The original function is assumed continuous here. So if it's not continuous, then the point's not going to be a max or min because the point wouldn't exist in the first place. So assuming your function is continuous, we can do either one of these two tests. You don't have to do both, it's either or, to figure out where your maximums and minimums are. So the first derivative test says, in step 1, we're going to find the critical points. Right? And remember, this was where f prime was equal to 0 or undefined. We define those to be critical points based on what we know from Fermat's theorem. It's basically a two-step process. You test the critical points on an interval and conclude. Of course, you're going to plug it into the first derivative, and you're going to make a conclusion as follows, or based on the following. So here's one situation. Okay, so you have an interval which you're going to be plugging in numbers into this interval into the first derivative. Let's say you locate a point x0, that is your critical point. Alright, so from step 1 you find all your critical points, x0 is one of them, you plot it on a number line. What you're going to do is you're going to take values immediately to the left and the right of this. Okay, say you take an x1 and an x2. And you're going to plug those numbers into the first derivative. So we're going to find f prime of x1 and f prime of x2. And here's one possibility. Let's say we are positive here and negative there. What would positive mean? Derivative is positive means what?
function is increasing.
Function is increasing. So we know the function is moving up as you move from left to right. When the derivative is negative, of course the function is decreasing. So we're passing through a point that's a critical point. The function is continuous the whole time. We're increasing on the left of the point, we're decreasing on the right of the point, so that means the point would be what? It would have to be a maximum. Under these conditions, that would force it to be a maximum. Similarly, if we have our critical point, and we pick a random point on the left and the right of it, and I find the derivative over here, and it turns out it's decreasing on this side, but the derivative over here is increasing. That means it's going down on this side, but going up on that side, which means this point is going to be the lowest point. That's how you identify a minimum. So max occurs if your function is continuous, and at the critical point, you're increasing on the left, decreasing on the right. That gives you a maximum. Minimum is if you're decreasing, then increasing, and all other situations, it's neither. Unless possibly if it's on an endpoint, but it's never going to be on an endpoint. Usually when we're considering this, we're talking about the entire real line. So that's the first derivative test. We're using the first derivative. The fact that we know that the first derivative, the sign of the first derivative tells us about increasing and decreasing, we can put all these ideas together to figure out, oh, a maximum would have to behave this way, a minimum will have to behave that way. So that's the first derivative test. There's also the second derivative test. So this is, again, find critical points. And again, your function is continuous the whole time. So you find where your derivative is 0 undefined, and 2. You will test critical points. The second derivative. So again, everyone's continuous here, and it's very nice to look at what's going on. Well, here you don't test on an interval; you actually plug them in. So if x naught is a critical number, and we know that the second derivative, if I plug in x naught into the second derivative, and I get something that's positive result, versus if I plug in the number into the second derivative and get a negative result, versus what if I plug this into the second derivative and get a 0 result. Each of these will mean something different. What do we know about if f double prime is positive? What does that mean for the function? If f double prime is positive, what does it mean when f double prime is positive? Yeah?
It's about like if it concaves up or down or no?
Yeah, concavity, right? So what would this mean? Positive.
Concaves up.
Concave up. Up you're feeling positive, you're shaped like a smiley face. Right? So if the shape of the graph is like this, what would you expect it to be?
Minimum?
It has to be a minimum. So you can just plug the number into the second derivative, and based on its value, you can know it's a minimum. This one, if your second derivative is negative, that's concave down like a frown, which that will tell you that this is a maximum. If your second derivative is 0, you kind of no info, you kind of have to do something else. So that's the first and second derivative test. You can use either or. And this one, it doesn't really work at sharp corners. So in critical points here, this is where the derivative is 0. For sharp corners, it's not very useful. And usually we'll end up with a situation like this if it's a sharp corner anyway. But these are the two tests where you can locate maximums and minimums. Now the examples here we'll use in the next section anyway. We're going to be doing these kind of things anyway, so I think I'll save the examples for the curve sketching. So we're going to start the curve sketching now. And we're going to do this in the curve sketching examples. Usually when it comes to curve sketching, we're never going to have to ever use the second derivative test because this kind of analysis we'll have to do anyway. So we'll already have all the information for the first derivative test. But we're going to apply our knowledge from these two curve sketching. So you can refer to your handouts. Yeah. So these can be kind of hefty depending on the function that you're given, but I don't think I'll give you a crazy function, maybe a polynomial of some sort. So again, this is one of those things where there's a sequence of steps that you often have to follow, right? And I mean, other than the fact that 4 must come before 5, the order really doesn't matter, but I suggest this order. It sort of makes sense to do it in this order all the time. It's also something where if you do something in the same order, you get used to it so much that in a test you'll never be wondering like, what should I do next again? You'll know what you're going to do next because you always do the same thing next. Okay, so I recommend doing it in this order all the time, and it'll be very logical doing it in this order because when you get to a step, any information you need from that step you can actually garner from previous steps. So yeah, so these will be the steps to actually sketch a curve. So pretty similar to the kinds of things you do in pre-calculus, except we're going to be sketching a curve in a lot more detail. We're going to be able to locate points that we couldn't locate before and know about the shapes of graphs that we couldn't really know about before. But yeah, these are the steps you'll always go through. So one, you'll always want to know about the domain of the function. We studied that already, and that was on test 1. How to find the X and Y-intercepts would be the second step. That's also something we know how to find, right? You find the x-intercept by setting y equal to 0 and solving for x. You find the y-intercepts by setting x equals 0 and solve for y. Then you'll find the asymptotes. So maybe I'll just mention a little bit about that. There are two kinds of asymptotes here that we care about. There's the horizontal asymptotes and the vertical asymptotes. So the horizontal asymptotes, and this is kind of written down, but you're looking at what the limit at infinity of your function. So you find the limit as x approaches infinity and negative infinity of your function. It will give you some answer. And if L is a finite number, then y equals L is a horizontal asymptote. If you get infinity or does not exist, there is no horizontal asymptote. So if you want to figure out what your horizontal asymptote, and this is really describing, is there some horizontal line that your function will move towards as you go to infinity or negative infinity? So it's kind of looking for whether your function is leveling off somewhere is going to be the horizontal asymptote. Vertical asymptotes is if there's some sort of x value that your graph can't touch and it approaches it. So this guy kind of happens when you have an infinite limit as opposed to a limit at infinity. So if there's a point A, so we can look at this point A here, where I notice that if I take the limit as x approaches a from the left of f of x, it goes to negative infinity. Whereas here, if I take the limit as x approaches a from the right of f of x, it goes to positive infinity. When your limit as you're approaching a finite number is shooting off to infinity, it means there's some x value for which your graph is shooting up or shooting down. And what that means is it creates this kind of wedge here that won't, it will be an x value that you can't touch. Usually, we will have, when this actually applies, we will have a function of the form, some sort of ratio. And we can find vertical asymptotes by setting the denominator equals 0. Right? So we know that that's usually when things like this happen. Division by 0 is something that will create this kind of x value that you can't touch, so your graph can only approach that x value but can never actually get to it. So that would be the usual case here. There are a lot of considerations here, but we won't do any of the complicated ones. Usually if a vertical asymptote is applied, it's going to be because it's a rational function or something. And you need to set the denominator equal to 0 to figure out what the bad points are that you can't touch. And now we move on to the fourth step. Now the fourth step is to find the intervals of increasing and decreasing and the locations of local maximums and minimums. And that's sort of where the first derivative test comes in. That first derivative test actually tells you when it's increasing or decreasing because you're figuring out where the derivative is positive or negative. And you can identify maximum and minimums from that same chart. So the first derivative test really helps you with step 4. Then you're going to move on to the next one where now you're going to focus on concavity. We're figuring out the shape of the graph while it's doing what it's doing, and whether there are inflection points. So we'll actually examine the critical points of the second derivative in order to do that. So we'll do a similar test except we're plugging into the second derivative instead of the first to figure out the concavity. And after that we can sketch the graph. Right? So we're going to do a couple examples like A and B. And I think I've already decided, like, for the test, I'm not going to actually give you anything more complicated, like the guys at the bottom. So the lessons we can learn from A and B will be enough to do the problems that I'll be giving you. So there are two. The first one is something we know how to graph already. I just want you to see how we would graph it from scratch, but you should actually know what the answer should look like before. And then the second one is a little bit, you can probably figure, I don't know if you remember how much you remember from pre-calc, but you can probably figure out what that graph looks like as well. But we're going to graph it in a lot of detail, and so we'll do those two. So let's actually jump into it. So let's go through these 6 steps for parts A and B, and we'll see how they actually fit together to create the picture of this curve. So let's get rid of this. So these kinds of problems, they can be hefty depending on the function. So usually there will be like just one big problem where I say find all these things and sketch the curve, and it'll be like one problem on its own, like one big massive 20-point problem where you have to do all this stuff and sketch the picture. Okay. So let's actually go into it. Let's f of x equals 1 over x squared. Now we already know what this looks like, but let's actually build it up from scratch to figure out how this would look. So we start with step 1. Step 1 says we need to find the domain of this function. What's the domain of this function? Yeah?
The negative infinity references to 0, and then union with 0 to infinity.
Right, so anyone except x equals 0 can work, right? X cannot be 0. Okay, so that's your domain. And that's going to be important for you to consider later. But let's move on to the next one. Now we're going to look for intercepts. X-intercepts, Y-intercepts. Let's start with the X-intercepts. How do you find X-intercepts?
Set your original function equal to 0.
Set y equals 0, solve for x. So this means that 0 is equal to 1 over x squared. This means, what's the solution?
There's none.
No solution. Right. This means there are no x-intercepts. Right, this is a fraction. The only way a fraction can possibly be 0 is if the numerator is 0, but the numerator is always 1. It's never going to be 0. You could also, if you multiply both sides by x squared, you realize that this gives you the equation 0 equals 1. We know that's false. There is no xi that can solve this equation. So there is no x-intercept. How do we find y-intercepts in general? You set x equals 0, solve for y, right? But this guy is not in your domain, right? From by step 1. Which means there's no y-intercept either. So we can know the graph of this guy is a guy that has this domain and there are no x or y intercepts. Let's move further. So the third step would be where we find asymptotes. Let's start with the horizontal. So I'm going to find the limit as x approaches infinity of my function. Limit as x approaches minus infinity of my function. What's the limit as x approaches infinity of this guy?
0.
0. And what about minus infinity?
Same thing.
Same thing. This means that y equals 0 is the horizontal asymptote, because that's a finite number. By the way, for rational functions, these are functions where the top and bottom are polynomials. These will always actually be the same thing. But in general, they're not the same. Let's talk about vertical asymptotes. So again, there's a shortcut here. Just set the denominator equal to 0. So this means that x squared equals 0. So x equals 0 is a vertical asymptote. That'll be an xi that you can't touch, and that makes sense because it's not in our domain. So this is a function that has no x or y intercepts, but it has a horizontal asymptote of y equals 0. It has a vertical asymptote of x equals 0. Let's move on to step 4, which I want a little bit more space.
John,
Yeah.
sorry, can you just explain again why the asymptote is y equals 0?
Oh, because I'm saying as I move to infinity, my y value is approaching 0, right? Which means the graph is getting closer and closer to 0. So then, once I find the limit as x approaches infinity and I get a number, that means there's some y value number that I approach as I go to infinity. Right, so that's why this 0, or whatever, if that gives me a value, that ends up being the horizontal asymptote. You're telling me a value that my graph is getting close to as I go to infinity. And because it's a limit, it's talking about the y value, so it tells you how horizontally it's behaving. But you always find these two limits for horizontal asymptotes. If you get an answer, a number for an answer, then that's it. If you get infinity, or you get does not exist, then there's no horizontal asymptote. We're saying f of x equals 1 over x squared. Let's move on to step 4. Now in step 4, we found where it's increasing, decreasing, maximums, minimums. We can get all of this with one kind of setup. So we'll do all 4 at once. So it starts out by doing the first derivative. So our f of x here is x to the minus 2. And I mean, at this point I would expect everyone knows how to find derivatives very well, so I'm just going to do it. So there'll be that, which in other words is this guy. So now I need to find the critical points. That means I set this guy equal to 0 or undefined. This one, no solution. This one is obviously undefined if x equals 0 because I'm dividing by 0. So that's your critical point. And I'm going to now test it on the number line in f single prime. And plot 0. And now you can pick any random point on the left and the right of 0. So let me pick -1, pick something easy since I can pick anything, +1. And I'm going to plug these two numbers into the first derivative, which is this expression. If I plug in a -1 here, do I get a positive or a negative? I get a positive because I get -1 cubed, which is negative, and I have -2 divided by negative. So it's going to give me a positive number here, which means increasing. If I plug in a 1 here, this function gives me a negative, which means decreasing. So I can conclude the following. We're increasing from -infinity to 0. We're decreasing from 0 to infinity. Do we have a max or a min? Max, min.
Max.
Where's the max?
0.
What does step 1 tell us?
0.
0 is not in the domain, so this cannot be a max. Under normal circumstances, if your function was continuous, it would be a max. But we know that it's actually not in the domain, so there is no max. Because x equals 0 is not in domain. Right, so that was the importance of step 1. So if you do step 1 and you realize there are some points not in the domain, but they show up as answers to other parts, you can know that, oh, those don't exist because it's not in the domain. And obviously there's not even a candidate for the minimum here, so there's none either. So you see we're building up a picture of this function. So we know there are no x-intercepts, we know, or y-intercepts, we know there's a horizontal asymptote at y equals 0, vertical asymptote at x equals 0. I know there's no maximum, no minimum, but I know where it's moving up and where it's moving down. Okay, let's get an even better picture. Let's move on to step 5. Now in step 5 we talk about concavity and inflections. And since I'm talking about concavity, it's going to be with the second derivative. So here I'm going to find the second derivative of our function. So I'm going to differentiate this term. Or that's just 6 over x if you want. It's not necessary to write it like that, but you can.
Isn't it -6?
No, because there's a -2.
Oh.
And so now, again, kind of like with the first derivative, I'm going to find the critical points for the second derivative. And so I'm going to set 6 over x to the 4th equals 0, or 6 over x to the 4th is undefined. And again, here there's no solution. And here x equals 0 is the only guy I have to test. So now I'm going to plug into the second derivative, and I'm going to test around 0, just as before. Try a -1, try a +1. I'm plugging in -1 into this guy. Notice that I get a positive number. If I plug in 1 into that guy, I also get a positive number. What does that mean here?
It's just increasing.
No.
Well, the rate of the function, the rate of increase in the function is increasing.
But what does that mean?
Is it concave up?
Concave up. And that means it's up like a cup. It doesn't talk about increasing, it talks about the shape of the graph, right? So it's like a smiley face. Similarly here, it should be a smiley face. Right, increasing and decreasing comes from the first derivative. So now I can again make some conclusions here. Where am I concave up? Where am I concave down? Are there any inflections? So notice I'm concave up on -infinity to 0, union 0 to infinity. I'm concave up everywhere. This is concave up, nowhere. Concave down. Are there any inflections? No. Right, because remember what an inflection is. It's a point where you switch from concave up to concave down. There is no switch that happens here. So there is no inflection. Okay. With all this information, we can now sketch the graph. So what we'll do is we're going to draw the axes. We're going to plot all the information that we found so far. And then we are going to draw a picture that obeys all these rules. So let's just drawing it large so you can see it. And so now you're going to start plotting things in, right? Starting from step 1 to step 5. Right? So 1 is just the domain, so we kind of know we have to avoid 0. Move on to step 2, intercepts. There were no intercepts, so we don't have to plot any points there, no intercepts. But there was a horizontal asymptote and a vertical asymptote, right? So how you write asymptote is you draw them on with broken lines. So technically they're not a part of the graph, but they are lines that you have to worry about because they will tell you what your function is tending towards. So you usually draw them with a broken line, and if it's on the axis, just draw it with a very dark broken line. If it was somewhere else, you would draw it with a very faint broken line, because technically it's not a part of the graph, it's a guideline. So that's y equals 0 is the horizontal asymptote. And then you do the same thing because x equals 0 is a vertical asymptote. So there's the same thing that's happening on the x-axis. Because x equals 0 is vertical asymptote. Now you move on to the next step. In the next step we talked about increasing, decreasing maximums and minimums. And we found where it was increasing was what? Negative infinity to 0, right? So what I like to draw is like this little interval thing. So I can say from this point going back, we're increasing. And from this point going forward, we're increasing. And you'll see the importance of this kind of interval later on. We also knew that from this point going back, it was concave up. And from this point going forward, it was also concave up. And there was no inflection. No max, no min. So at this point, all the information that I found from step 1 through 5, I put it on the axis. So now I can just forget everything else and just draw what I should see here. Now, this one might present a challenge at first because you realize that there are no points that are plotted, so I don't really know where my graph should be. What point should it be going through, right? So, yeah, do you have a question?
Would it be decreasing going this way?
Oh, yeah, we found it to be decreasing. But other than that, we don't have any points here to see what the thing is passing through, which is kind of weird. So in a case like that, what you can kind of do is you can kind of figure out where your graph is going to be. Just through sort of a little bit of trial and error, but it'll be quick to figure out where you should be. So you might say, can my graph ever be down here? Right? So is it possible for me to be decreasing concave up down here? Now what would the consequences of that be? It turns out the answer would be no. Does anyone see why it would be no? Why is it impossible for me to be there?
Is it because it's concave up? Or no, because the asymptote is there?
So what would be the problem? So I can be concave up and be decreasing. Why would that not be a part of the graph?
Because the asymptote? Or no?
Because the asymptote.
Yeah.
if I keep decreasing forever, how am I going to approach 0 as the asymptote? There's another problem. If I start this and I follow that curve, what's going to happen? I'm going to create an x-intercept. I know there's no x-intercept. So I know automatically my graph cannot be down here. It has to be over here. So if my graph I know is up here, what would it have to behave like? Well, it has to be decreasing in concave up, so it has to have this kind of shape here. I also know that as I'm going to infinity, I'm approaching this one. So my graph would have to have this sort of behavior here. Right? So it's decreasing concave up, and it's approaching the horizontal asymptote. Of course, here, that will continue, and it will be like asymptotic to the x-axis, because this is a vertical asymptote, so I should be approaching there as well. Move to the other side, a similar kind of analysis happens. You ask, could I be down here? The answer is no, because I would have to look like this. I would create an x-intercept, which I know there shouldn't be. Also, the tail will never come back up to hit that, because it's always going to be increasing. So it means the graph would have to be up here. It would have to be approaching y equals 0 from this side, and approaching, well, this should be sort of symmetric, but anyway, and approaching x equals 0 from that side. And we obtained the familiar graph, right? But really, notice that we were obeying what was happening, right? In this region, we're increasing and concave up. This graph obeys that. There is no x-intercept, there's no y-intercept. Over here, we're decreasing and concave up. No x-intercept, no y-intercept, and we obey the asymptotes. Right? So this is the picture that fulfills all the pieces of information that we've had before. All right, but that's the graph that we're sort of familiar with. We kind of know that had to be the answer. Well, let's do it again. Right here, we had a bunch of nothings. So let's do an example where we have something to actually plot, so you can see how these things actually work. Let's move on to example B. Now example B is going to be longer, but it has a lot of lessons for us in example B. It has no asymptotes, but it'll have everything else. Let's do, for example, B. It's for exclude. Sorry. So the question would be phrased similarly to how you see this. Consider this function, find it in where it's increasing, where it's decreasing, the maximums and minimums, blah, 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 and sketch the graph, right? So it'll be a question that asks you to do all these things. Okay. So immediately you jump into the 6 steps. The first step is to talk about the domain of the function. What's the domain of this function? All real numbers. Why? It's a polynomial, right? So now I know all x values are permitted, which means as long as I find a graph, if something looks like a maximum, it's a maximum, right? There's no x value that I have to avoid. Everything will work. 2, move on to intercepts. Let's try to find x-intercepts. This means you're going to set the y equals 0, solve for x. How do I solve that for x?
Factor out of x squared. And then use that rule that like x, you factor that, the x squared minus 4 to x plus 2 to x minus.
Difference of squares. And so if a product equals 0, then each one of the factors must be 0. So I get x equals 0, or x equals 2, or x equals minus 2. So I know I have 3 x-intercepts. Okay? Which means when I start drawing my picture, whatever I'm doing, I need to make sure I touch the x-axis 3 times. No more, no less. There are 3 points at which I must touch the x-axis. What about the y-intercept? since you said x equals 0, solve for y. So that means your y would be 0 to the fourth minus 4 times 0 squared, which is 0. So y equals 0 is the y-intercept. Which makes sense, right? If the x equals 0, the y must be 0, because that's what we curve. So this guy has intercepts. 3. Asymptotes. Where are the asymptotes? What's the limit as x approaches infinity of this?
Is it
Infinity. And negative infinity of this? Still infinity, right? So it's infinite. You don't get a number. No horizontal asymptote. Vertical asymptotes occur when there's an x value you can't touch. Are there any x values you can't touch? No. So there are none. By the way, this will always happen for a polynomial. Polynomials don't have asymptotes. So that's just something you can skip with a polynomial. So that's the asymptotes. So next thing we move on to 4. There are none. Step 4, increasing, decreasing, maximum, minimum. This means we're going to find the first derivative. Find the critical points. And I'm going to set this guy equal to 0 or undefined. Obviously no solution, that's a polynomial, it's always defined. But if it's equal to 0, how do I solve that?
factor out 2x?
I can factor out 4x. I would have x squared minus 2 equals 0. And that would be, this is 4x times x minus radical 2 times x plus radical 2 by a difference of squares. And so I get 3 points as well here. X equals 0, x equals radical 2, or x equals minus radical 2 are my critical points. I'm going to test those on a number line. 0, minus radical 2, positive radical 2. So there are 3 critical points to test here. And you test them in the first derivative. You also test in between these intervals. So something immediately to the left and to the right of each one of them. So I can pick a number in here. For example, minus 1 is in here. Minus 2 is out here. 1 is in here. And positive 2 is out here. How would you know? You can plug that into your calculator and you'll realize that the radical of 2 is 1.414. So you know your 1 is less than it and 2 is bigger than it. So it's between 1 and 2. And we're plugging these values into the first derivative, which is this guy. It's going to be easier to do it in the factored form. So let's go with minus 2. Plug in minus 2 into the x, you have a negative number. Plug in minus 2 here, you have a negative number. Plug in minus 2 here, you have a negative number. So that's a negative times a negative times a negative. And it's negative. So that tells you I'm decreasing here. Do the same thing with negative 1. Plug it in x, that's a negative number. Minus 1 minus radical 2, that's a negative number. Minus 1 plus radical 2 is actually a positive number. So I have a negative times a negative times a positive. That's positive, which means I'm increasing. The same thing for 1. Positive number. 1 minus radical 2 is a negative number. 1 plus radical 2 is a positive number. So it's a positive times a negative times a positive. That means it's negative. It's decreasing. Plug in 2. So this would be positive number, positive number, positive number, positive times positive times positive, is positive, this up. Alternatively, you could plug the numbers into your calculator, but if you wanted to do it in your head, it's much easier to do it in the factored form. And this kind of starts to create some sort of picture for us, but let's actually summarize what it tells us. Where are we increasing? Where are we decreasing? Where are their maximums? Where are their minimums? Where are we increasing? On the intervals where the arrows are pointing up, so that's on this interval, to minus radical 2 and 0, union this interval, radical 2 to infinity. We're decreasing where the arrows are pointing down, so minus infinity to minus radical 2, union 0 to radical 2. Can you see where we have a maximum?
At 0.
0.
0 is going to be a maximum, right? And it's defined at 0 because the domain is all real numbers. Minimums will be here and here. So we have 2 minimums and 1 maximum. So here our maximum happens at 0, and we know that our y value is also 0. So 0, 0 is going to be a maximum point. Minimums occur at minus radical 2 and positive radical 2. This means your y values will be, how do I find the y value when my x is minus radical 2? Into the original function is where you plug that in. So you can do this in your calculator, but this is also easy enough to do by hand. So this raised to the 4th power, I know radical 2 squared is 2, and then I raised it squared again, so that's going to be 4. Radical 2 squared is 2 times 4, that's 8, so it's a minus 4. Because those powers are all even, whether I plug in the negative or the positive number, I'll get the same thing. So I have these 2 points. Minus radical 2, comma minus 4, and positive radical 2, comma minus 4. These are my minimum points. So we're getting a lot of traction out of this one, so we can find both maximums and minimums. Still one more level to get through before the picture. So the 5th step, Cavian inflections. Here we're going to find the second derivative. This is the derivative of the derivative. It's going to be 12x squared minus 8. We're going to find the critical points of the derivative. So I'm setting 12x squared minus 8 equals 0, or undefined. Realize for undefined there's no solution, it's a polynomial. If it's equal to 0, there's a common 4 I can factor out. So my x would be, move the 2 to the other side, divide by 3, and take the radical. Those are the 2 points I'm testing in the second derivative. I'm going to plug in some random numbers now. 0, minus 1, and 1. Right, 2/3 is less than 1, you take the radical, it gets even smaller, so it's going to be 1. 1 is bigger than it. And we're plugging these numbers into the second derivative, which is this guy here. If I plug in a 0, I get minus 2, so that's negative. If I plug in a minus 1, that's 3 minus 2, that's positive. Plugging in positive 1 will give me the same thing. So what do I know over here? What's this?
Increasing? No, concave up.
Concave up, right? Second derivative doesn't tell you about increase, it tells you about concave up. So this tells you the shape is a smiley face. Negative means the shape is a frowny face. And positive means the shape is a smiley face. Let's summarize that real quick. So concave up, concave down are their inflections. So where am I concave up? These two intervals here. Concave down in the middle. Any inflection points here? Two.
Like 2 inflection points?
Okay, and here, right?
Yeah.
Notice that this is a point where I was concave up on this side, concave down on that side. The second derivative switched signs, so that's ending up an inflection point. So is this an inflection point? So we're two of them. Positive and negative, but in the original function, they'll give me the same y value. So there's x at minus radical 2/3 and x at positive radical 2/3 are inflection points. This one would tell you the y value is minus radical 2/3 fourth minus 4 times radical 2/3 squared. So if you square this, you get 2/3. Square that again, you get 4/9 minus. You square this,
Minus
8/3, which is what? 24/9. So it's minus 20 over 9. And so there are two inflection points. That's minus radical 2/3 minus 20 over 9 and positive radical 2/3 minus 20 over 9. Copy that down and then we'll draw the picture. Yeah?
Okay, why do you just plug the negative out of 2?
Because these are even powers, so the negative and the positive will give you the same answer,
Same answer
for the x value. Yeah. Yeah, if the powers weren't all even, then I would have to try both, but in this case it's the same. Okay, so hopefully you guys remember the answers, because I'm getting rid of them. So let's actually draw this behemoth. A guy that has everything except asymptotes. And then we're going to do something that has everything. I'm kidding. I mean, we're done after this one. But let's actually just see our creation. So now we're going to start again plotting everything on this graph. All the information from the previous 5 steps we're going to put on this graph and then get to the picture. So domain was everything, so nothing really to say there. Everywhere can work. Intercepts, were there x-intercepts?
0, -2,
So I'm going to put those in. So 0 is an x-intercept. -2 is an x-intercept. And +2 and -2. This should kind of be symmetric. Okay. Y-intercepts, there was only one, which is here, coincides with that. So those are the intercepts. So I plot the intercepts. Then you move on to the next one. The next step was talking about asymptotes. There were no asymptotes, so I don't have to worry about it. The next step was talking about increasing, decreasing max and mins. Where was I increasing?
Between -2 and -√2, where you're decreasing.
You mean negative radical 2, right? And positive radical 2?
Yeah.
So I'm going to write that here. So from negative radical 2 back, what am I doing?
You're decreasing.
Decreasing. Right, and this is drawn very faintly. This isn't a part of the graph, it's just me trying to put all the information on something. Where am I increasing?
Negative radical 2 to 0.
So I'm increasing here. What am I doing here?
Increased.
I'm still increasing?
No.
Between 0 and radical 2.
You're decreasing.
I'm decreasing. And from here to back?
Increasing.
Increasing. Any maximums or minimums?
It's like 6 equals 0.
This was a maximum. Minimums?
Negative radical 2 and negative 4.
Okay, so this is a minimum. I know it's going to be the smallest point, so let's put it way down here. Label that as a minimum. So this would be like -4, you said?
Yeah.
And so this here, coming down here, that's also a minimum. Okay, so I labeled that on my graph. And that's it from that section. Now move on to the 5th section, concavity. Where are we concave up?
Negative infinity to negative radical 2 over 3. And
That's where I'm concave up?
yeah.
Okay, so let me just put up a point here. Negative radical 2/3. So from here back, I'm concave up. Where else am I concave up?
Positive radical 2 over 3 to infinity.
Positive radical 2/3. Just up here, all the way to infinity. Concave up. And in the middle, I'm concave down, right?
Yeah.
Concave down. Any inflection points?
Yeah. At negative radical 2 over 3 and positive. Like, yeah.
I think it was minus 20
Negative-
over 9 or something.
Yeah. Yeah.
Okay, so that here I know is an inflection point. And similarly over here, I know that's an inflection point. That's all the information we have, right? So you can sort of see this picture building. So I know the picture I'm going to draw has to pass through all these points. I know the behavior it should have while passing through the points. So passing through the minimum, it has to look like that, like a valley. When it passes through this point, it has to be a maximum, it has to look like that. When it's passing through either of these points, I need to be switching concavity. I need to switch from a concave up to a concave down at this point. At this point, I need to switch from a concave down to a concave up. Then I know over here, I'm increasing concave up, so I should shape like a smiley face while moving up. Over here, I'm decreasing concave up, so I shape like a smiley face while moving down. So let's actually draw that. So I'm shaped like a smiley face moving down. And I need to pass through these 2 points. So that's the first part of my graph. Right? Decreasing concave up in this interval, I need to pass through those 2 points. Now I move over here. Notice I'm in the section where I'm increasing. And I'm still in the concave up section. So now I start increasing concave up. So over here, decreasing concave up. Over here, increasing concave up, because that's what these intervals are telling me. Move over here, I'm still increasing, but now I'm in the concave down region, so I'm increasing concave down. So here I'm going to switch concavity. See here I was a smiley face. I pass through this point, I'm now a frowny face. Now over here, notice now I'm decreasing and I'm still concave down. So I'm decreasing concave down, so I'm decreasing shape like a frown, and here I'm still decreasing, but now I'm in the concave up section. So I'm decreasing concave up, I shape like a smiley face. Notice that here there's an inflection that happened. So now I'm a smiley face. And finally, we're in the last section. We're increasing concave up. And I need to pass through these 2 points, so my graph's going to look like this. So then I get a W. So the graph's just a W, which is a very particular kind of W. The curve has to be concave up like this whole time, concave down this whole time, concave up this whole time. It's passing through all the coordinates that I know. It's a minimum where it's supposed to be minimums, maximums are supposed to be, and inflections happen here. I switch from concave up to concave down, from concave down to concave up. And so that would be the end product. So we'll stop there. I think we have homework for 4.1 and 4.2.
And 3.6.
And 3.6.
Yeah.
So leave that here and relate exponential growth and decay and related rates. Yes.